Okay, we're recording. Excuse me. So it turns out that substance x equals c in f of x, when we want to find the limit as x approaches c, works not only for polynomials and rational functions, but with many other functions. So trig, log, exponential functions, compositions, mixture of functions. Always try substitution first. So in the homework on 7 through 14, that's what you guys did. So like in example number 7, that looks kind of weird, x times sine x. Well, we'll just substitute, right? Try substitution first. Pi over 2 times sine of pi over 2. Hopefully you remember your unit circle. That's why we had that review on the summer assignment. Sine of pi over 2 is 1. The answer is pi over 2. And again, if you guys ever need resources on any pre-cal type stuff, just ask. I have lots of stuff. Again, I've taught virtually every course at this school, except regular geometry I've never done. Pre-cal BC honors I've never done. I haven't done AP Calcs BC, but I've tutored all those subjects. Yeah, but I've taught pretty much everything else. So I have plenty of resources if you need them, just let me know. But anyway, sometimes that works. Let's try it again. Look at 8a. You're just going to do root 4, which is 2, or root 0, which is 0. And if you were to graph y equals root x, there's definitely a point at 0, 0. Definitely a point at 1, 1, and definitely a point at 4, 2. So graphically, we could see that if I'm approaching 4 from the left or from the right, y is converging towards 2. And for x equals 0, you can only use a right-handed limit. But, you know, it's going towards 0 anyway. But be sure that the limit actually does exist. You know, so sometimes it helps to look at the graph. So you have to be sure. Really what I'm telling you to do is look at the graph. And try plugging in numbers close to what x is approaching. So, yeah, just be sure that that actually exists. You guys get, I can see you guys are furiously copying stuff, so I'll give you guys a second to do that while I just check some of the notes here. Okay, we'll keep moving. Any questions so far? Nope.
So
yeah, go ahead. Fire away.
So if you're doing substitution, you basically always should graph it after just to make sure.
Yeah, it's really quick. Yeah, I mean, once you get very good at this, you usually don't, but I think in the beginning, because you guys are just getting used to this stuff, yeah, I would suggest that. All right, now the fun begins. All right, this is the part I love. So sometimes substitution will fail you. So if I were to substitute for example 9, obviously an E is missing there, little typo. If I do 2 squared minus 4 over 2 minus 2, I get 4 minus 4 over 0, 0 over 0, and that is a problem. So important, if substitution leads to does not exist, it does not necessarily mean that the limit does not exist. It just means the substitution does not work. So very, very important. Don't assume that the limit does not exist if you get 0 over 0. And actually, I probably should have this discussion right now. So I think sometimes we just kind of assume certain things, or we just, because you guys are told stuff, you guys don't question it. But let's get a little bit details. It shouldn't take me too long to explain. And if I have to explain it again, I'm totally happy to do that at a later time. 1 over 0 and 0 over 0 are actually different things. 1 over 0 is called undefined. 0 over 0 is called indeterminate. Does anyone know why those are actually different, and why we use different names for them, and why you use those specific names? If anyone wants to chime in, I'm totally happy to hear what some perspectives might be, because my perspective could be sometimes a little bit could be corrected too but I think I'm right with my explanations. Well, let's explain undefined. It means it's not defined. There's no definition. So 1 over 0 doesn't equal, I don't know what that is. Well, actually, it can't equal anything. 1 over 0 is impossible. So undefined really means impossible. Indeterminate means we don't know. And there's actually a difference between those two statements. Let's think back in the day. You don't have to write, you can just relax. You don't have to write this down if you don't want to, but I'm recording it. 10 over 2, we know that's 5, right? Because isn't 2 times 5 equal to 10? Yeah. If I were to multiply this to 5, I get 10, right? What if I have 10 divided by 0? Well, I don't know. 10 equals 0 times some number. What can I multiply to 0 to make it 10? Absolutely nothing. Nothing times 0 is ever going to equal 10. Anything times 0 is what? 0. That's it. So this is impossible. You can never, ever divide a non-zero number by 0. Just can't do it. Notice I use the word non-zero number divided by 0. So a non-zero number divided by 0 is impossible, because I'm not able to do the inverse of it, right? I'm not able to multiply this denominator by whatever that's supposed to be and get it to equal 10. That's impossible. Now, 0 over 0 is indeterminate. Why is that indeterminate? Well, 0 over 0 could equal this. I totally made up that number. Why? What if I multiply 0 to that? What's 0 times 4.654? 0. Or it could equal negative 102.587. I have no clue. It's indeterminate. So 0, 0, it's not necessarily undefined. It's just something we just really it's vague. We just don't know. So that's why you can't give up if you get 0 over 0 when you do substitution. It's indeterminate. So it just means substitution doesn't work. So we got to try something else. So that's just a little bit of a number theory discussion. So if you have any questions about it, we can always talk later. But 0 over 0 is called indeterminate for that reason. We just don't know. So what could we do? We could do tables. You could like plug in like 1.999, 2.001. You could do all that jazz if you wanted to. And actually, I'll do it really quickly. So let's see here. If I did x squared minus 4 divided by x minus 2, alpha trace y1, 1.999, 2.001, I get these values. The numbers are pretty darn close to 4. So I suspect my limit's going to equal 4. If I were to graph it, you probably will see something that looks like a linear function. So you'll probably get that. But here's what I actually will want you to do. We spent all the time on the summer assignment with factoring and simplifying. You spent all this time in middle school doing this stuff. Now you're going to use it. If I factor it, I could rewrite it like this. Again, the graph, which I didn't realize I had a quarter plane here to use, looks like that. There's a hole there because these go away. Remember, when you cross off factors, that leads to a hole, not an asymptote. Asymptote would be if nothing goes away and whatever makes the bottom 0 is an vertical asymptote. And we're going to actually get into that more deeply next week about vertical asymptotes. But so that's just y equals x plus 2. So really now you're just doing the limit. Actually, let me do it down below because I have space for that. You're doing the limit as x approaches 2 of x plus 2, which is going to be 4. And that's it. That's what we got. Any questions so far about what I've done?
So is it basically kind of like you're factoring it and simplifying it until you can substitute, or
Yes,
until you're able to?
Yes. And trust me, I designed these problems very carefully so that will happen. I'm not going to give you a problem where you're going to get to a dead end. I want you to actually find the answer. The AP does that. The textbooks do it. I will say writing problems actually is probably the I love it actually. That's one of my favorite things to do. But it takes my most of my time. So they always say like English teachers, because they spend all the time grading papers. Yes, grading for English history is more time-consuming than any other grading for any other subject. But I would argue that writing a test is harder in math than it's for any other subject. Because writing in English or history test, you just say, hey, just talk about the Civil War, or talk about Charles Dickens novel or something. You have to carefully engineer these problems. So I will carefully engineer so that they'll work out nicely. So this question, does this factoring only come after we've checked that? Yes, exactly. After we check that we can't substitute, then we try factoring. Factoring is one of the things we pull out of our back pocket. Say, okay, I can't substitute, let's try this, right? So yeah, so the example that illustrates, that kind of is a great comment. Factor, cancel common factors, then try substitution again. If you see an opportunity to factor, please take advantage of that opportunity. And then cancel out. Okay. We get to have even more fun in the next page. Are we ready to move on to the next page? Yeah, cool. Let's do it. Okay, next page. All right, these are a little intense. So we're going to try substitution again. Oh, the great question. What if you factor and there are no common factors to cancel? In that case, we just would have to say the limit does not exist, or we can we try other methods if it's not if there's not something that's factorable. That's why I think you should always graph first or plug in numbers first to kind of see if there is a limit. Because if factoring doesn't work, then maybe there's another technique that will work. But if you exhausted several options and you actually could factor and nothing cancels, then sometimes we just have to just say, hey, it does not exist. And trust me, once we get through all these types of situations, you'll know when you can make that conclusion. But ultimately, yes, if you try all these things, but But graphically, you'll be able to see it too, right? Like you might be able to see something kind of like this. Like maybe I got like some sort of weird function that does that. And yeah, ultimately you're going to be able to say, yeah, it does not exist at this x equals c value. Okay, so let's look at example 10. If I plug in 0, I get indeterminate. Let's look at example 11 as well. If I plug in 0, also get 0, 0. So 10 and 11 are going to be pretty interesting. Because if you actually were to graph these, if I were to go to Desmos right now, so let me do root x plus 1. Or do y equals square root of x plus 1 minus 1, that all in parentheses, divided by x. And for approaching 0, it does say undefined there, but it's pretty close to like half. It looks like it's pretty close to 0.5. Or for the other one, if I do y equals 1 over x plus 3, divided by x. So I'm looking at my other computer screen. That's why I have two screens going on here. So the green curve, if I get close to 0 there, it looks like it's, it says undefined at 0, but looks like it's close to like negative 0.11, like maybe like 1/9 perhaps. So I suspect, going back to my notes again, that the answer for number 10 is probably going to be 1/2. Look at that's probably going to be negative 1/9, because that's what I saw graphically. So yes, I think you guys should graph, because you guys are still, this is new to you guys. But I mean, someone like me, I've done this a long time. I kind of trust the process. But you should graph just to be sure that that you see a limit. So this is what I'm expecting as my answers now. And I give you the answers in the homeworks. I don't care. In fact, there's something called Slater. I know about Slater. I'm just going to call it out. You guys have that as an option. But we want to make sure we understand the algebra that goes into it. So it's good to know the answer, but can we go through the process to get that? So that's what we're going to do right now. The number 10 is not going to be 5. It's going to be 1/2 because we got 0.5. Remember that. But let's go through it right now. So the one thing, I kind of take a deep sigh here. You can't be lazy. You have to keep writing the limit notation on the AP exam. If you don't do that, they actually will take out points. We actually have to keep writing the limit as x approaches 0 until you're finally ready to substitute. Because otherwise, then you're just writing this, which is not what we're intending to do. We're intending to do a limit. So you actually have to keep writing the limit notation. Just keep that in mind. So we're going to do something kind of fancy here. You're going to have to get a little creative. I'm going to multiply both top and bottom by root x plus 1 plus 1. So take a second and think about what I'm doing here. I'm multiplying both top and bottom of this fraction by some weird kind of expression, but the same expression, both top and bottom, because it's fair treatment, obviously. You guys remember this back in the day when you guys had these kind of problems? You guys remember doing this a long time ago? You had to rationalize? We made you guys do that, and we said, oh, just do it. The reason why is because we want you to understand this process of removing radicals. There was actually kind of some method behind that madness. Or maybe you might remember these kind of problems, like if you had like root 2 plus 1, you multiply top and bottom by, or sorry, if you had 1 plus root 2, remember we made you guys do all this stuff back in the day. We told you, we're rationalizing the denominator. Honestly, who gives a crap? You're rationalizing the denominator. It really doesn't matter. We just want you to get to know that this is a process you can use, because we're going to use that over here. Like, you know, when you guys do like a trigonometry, when you do like the sine of 45 degrees, it's root 2 over 2, 1 root 2, tomato, matter. But again, we want to make sure you understand rationalization. So if I do that, here's what's going to happen. You have the limit as x approaches 0. So if I FOIL, so there's a lot of algebra going on here. If I FOIL, multiply this by this, multiply that by that, multiply that by that, multiply that by that, what's going to happen? We have x plus 1 minus root x plus 1 plus root x plus 1, and then negative 1 times positive 1 is negative 1. What happens to the radicals now? Sorry, that's supposed to be a plus there.
They go away.
They go away.
Cancel out.
That's the whole point. At the bottom, of course, is just this. No need to distribute to x, because we're going to substitute anyway, so don't bother. The whole point is to get things to cancel. That's why we taught you guys the whole rationalization stuff. And actually, the 1 and negative 1 cancel out as well. So now I got the limit as x approaches 0 of x all over x root x plus 1 plus 1. More will cancel out. The x's cancel out. We want that to cancel. So now you take the limit of 1 over root x plus 1 plus 1. Can I substitute now? Absolutely. And you get 1/2, which is exactly what I got graphically. So the trigger, if you see a square root, try this process. Obviously, I can't factor here, so factoring won't work. But this is another thing I can pull out of my back pocket. So what we're doing is we multiply numerator and denominator by what we call the conjugate. Of the radical expression. The conjugate is when you switch a sign of the radical, or you switch a sign of something. Actually, I switch a sign of from negative 1 to positive 1 over here. So that's what we do. So that's a process, and you'll have a chance to practice this later today. I'm going to put you guys in a breakout room just a little bit so you can practice this skill. Let's try this again. For example 11. If you have any question about example 10 before I move forward. Remember, the algebra sometimes can be a little messy. But I'll be straight with you guys. The calculus is not hard. It's the algebra that's always the hardest part. That's usually where people tend to get tripped up. So, you know, if you need some time to follow the algebra, please let me know. I'm more than happy to re-explain stuff. And that's why we're recording, right? It's a good thing we're recording. Oh, why did I plug in 1? No, I didn't plug in 1. What I did was I replaced the x's here. X over x becomes 1. And then I plugged 0 in for x over here, right? I plug in 0 for x over here, and that's root of 0 plus 1. Let me actually erase this here. So remember, we had x plus 1 in here. And I replace that x with 0. And I'm doing root of 0 plus 1, which is 1. So I didn't plug 1, I plugged in 0 for x. But of course here, I replaced x with 1. So hopefully that cleared that up. All right, let's move on to 11. So the answer is negative 1/9. So what technique am I going to do here? Again, don't get lazy. You have to write the limit notation until you finally are ready to substitute. Well, I'm just going to find the LCD. The LCD is 3 times x plus 3. So the bottom stays as x. And you're going to have to multiply these two, you're going to have to add these two fractions by finding the least common denominator. And I see a question, I'll get to that in a second. But you're going to multiply this by x plus 3, x plus 3. So we know how to add fractions. We made you guys do this so many times. Now you kind of see why we made you guys do it. It's something we have to use, a skill that hopefully has been well developed. Oh yeah, great question. When you write your answers, just write 1/2. Yeah, for the previous question, nothing fancy. Just say it's 1/2. That's it. Just a number. Yeah, no need to be fancy. Anyway, so we're gonna combine these. So we have a complex fraction. So what I'm probably gonna do, probably off to the side here. Kind of like, I've never worked in a car, but when someone like works on an engine, maybe they pull the engine out, they're working on a little part of it and working another part off to the side. That's kind of what we're doing here. Like this is the engine, we're just taking a little bit of it out and we're just gonna work it out. So it's gonna be 3 minus parentheses x plus 3 over 3x plus 3. So I'm combining these two fractions. That's 3 over 3x plus 3 minus x plus 3 over 3x plus 3. So you have 3 minus parentheses x plus 3, which is 3 minus x minus 3, which means these cancel. So you have negative x over 3x plus 3. So all that numerator stuff became that. Give you guys a chance to kind of mull that over. Okay, any questions so far of what I've done? All right, so let's bring it all back. So the limit.
Why is it 3 times x plus 3 on the bottom and not 3x times x plus 3 on the bottom?
Oh, you mean like 3x plus 9? Or
Like when you substitute, it's like I got 3x times x plus 3 for the bottom because there's an x in the denominator.
oh, I'm going to get to that. I haven't got there yet. All I did was I just worked on this part right here. Does that make sense? Yeah, I just worked on that part. I haven't divided the x yet. I'm going to get there. So I have negative x over 3x plus 3. And the bottom is just straight up plain old x. Now, I could say that's x over 1, right? Anything can be divided by 1. So again, all I've done so far is just work on 1 over x plus 3 minus 1/3. The extra x over here, I'm now gonna deal with it. So now I have two things I'm dividing. So it becomes a fraction division problem. Negative x over 3x plus 3 times 1 over x. Because the x over 1 flips. And we get cancellation. So now it's going to be the limit as x approaches 0 of negative 1 over 3x plus 3. So now we're ready to substitute and get our final answer. If you do, you get negative 1 over 3 times 3, or negative 1/9, which is what the Desmos graph showed us. So to recap, I combined 1 over x plus 2 with minus 1/3. I did it off to the side here using LCD. When I got a single fraction, I brought it back into play. and had it over x, which is what we had originally. When you divide by x, the same thing as dividing by x over 1. So treat x as a fraction, just have put 1 in the denominator, that's fine. Flip it, because that's what you do with fraction division. You see an opportunity to simplify, that's going to be the big part. The x's go away, you have a new expression, now you can substitute, and now you can get your answer. So you'll have a chance to practice this as well. Any questions about example 11? Just to summarize, let me just pull something here. One second, just pulling it up here real quickly. So just to summarize really quickly, what you want to do is you want to simplify complex fractions into a single fraction. That's kind of the key takeaway. That's what we want to do. Okay, I think now is a good time for you guys to go in breakout rooms and practice. And actually, I'll kind of make my way to each room to see if there are any individual questions. So let me clear this. Let me pull up worksheet 3. Actually, before we do that, let's just kind of revisit, as I said, the big ideas in the weekly discussion topic. So our big ideas again. The concept of limit is one of the fundamental building blocks of calculus, and it was described with precision how change in one variable affects change in another. Okay. Instantly, we show how to define calculus limits of function values. The calculus rules are straightforward. Most of the limits we need can be found by substitution. We've done. Graphical investigation. We've done. Numerical approximation. We've done. Algebra. We've done. Combination of stuff. We've done. So we're getting there. And then one of the uses of limits in, that's a typo, in building, one of the uses of limits is building a careful definition of continuity. We're going to get to continuity later in this unit. That's a typo, I need to fix that. So anyway, and then if we look at our weekly discussion topic, which I changed the deadlines for that, so you can have your first one ready by Thursday afternoon, once you've kind of done a couple classes. And then you can respond to the others by the weekend. But yeah, how do we find a limit numerically? You know, how do we find a limit graphically? You know, so I want you guys to have that discussion. And why do we not care about specific y values? Because it's all about approach, right? So you'll have a chance to have that discussion. All right, worksheet number 3. See how far you guys can get today. I'm not gonna ask you guys to turn this in, just it's more for practice. But here you're asked to determine these analytically or algebraically. So try substitution first, if you can. You'll see that the first couple you'll be able to. But if you can't, then try some other methods like factoring or what we've just done so far. So I think you guys can actually get to these pretty quickly. I have faith that you guys can knock this out. So we'll spend maybe just 10 minutes, see how it goes. So worksheet number 3, you guys should have access to that. And let's do breakout rooms.